Okay, physical science time. We're going to talk about light. I don't know, part 2, I guess, because we didn't finish this yesterday. Electromagnetic waves. Is that even what it was called yesterday? I doubt it.
Yeah, electromagnetic waves.
Okay, electromagnetic waves, and what was the rest? And their properties?
Yeah.
And their properties.
Part 2.
Part
2.
2 as a Roman numeral. Oh, yes, part 2, electromagnetic boogaloo. Thanks, Justice. Very good. I'm having fun talking about light. The first thing let's talk about is we know about electromagnetic waves in general, and we just did a bell work about speed and wavelength and frequency. The speed of light, if you remember from yesterday, the speed of light is a fundamental constant of the universe that appears to slow down when it interacts with matter. So we talk about the speed of light in a vacuum, and there's an apparent deceleration when it encounters matter. Like that's what causes refraction that we see when I don't have a clear thing, but the speed of light. I'm going to use this. The speed of light is different in this than in the air around us, and so it appears that the light is slowing down, and that causes a lot of the properties of light. This is a nice cold bottle of water. But it's not actually slowing down, is it? Do you remember from yesterday what is in reality occurring? Yeah, it's absorbing and transmitting from each little particle, which makes its path longer. And so even though the light itself is traveling at the same speed, its average motion, its apparent motion, is slower. Light itself is broken up into different types of light. Someone still remembers the properties of the light that we had in the bell work, right? What was the final wavelength that you got?
6.81.
6.81 times 10 to the negative fourth, what? Meters. Okay, let's keep that in our pocket. And then we also had that its frequency was 440 gigahertz, right? Okay. Rainbow. I may not be able to make one. What are the colors of the rainbow, 7th grade?
Red,
I don't know. Someone says red. Hold on. Let's just slow down a little bit. Orange. Red, orange. Yes. Yellow. Yellow's good.
Green, blue.
Hold on. Yellow, green, blue. I do have all the colors. Blue. Some people, Isaac Newton and other people like him, are going to include indigo. Let's pretend that indigo here is purple, and then we're going to put violet as this pink, which is not really how it is, but that does look kind of cool. That looks pretty sweet, I think, if you ask me. Red, orange, yellow, green, blue. Okay. Do I need to label all these, or do you guys know about the colors, right? Label them red, orange, yellow, green, blue, purple. Okay, what do we call this little bit here? What's true about this light? What's true about the rainbow? What's true about the light that makes up the rainbow?
It goes from the shortest wavelength to the longest.
Okay, actually, almost the exact opposite. This here, we're going to put on this axis here, on my bottom y-axis. I'm going to put that this is increasing. Oops, I'm going to label this line itself. Actually, this line means increasing frequency. Increasing frequency as it goes this way. Looking at our equation, C equals lambda nu, if that way is increasing frequency, which way should I draw increasing wavelength? Well, what's true of frequency and wavelength? What must be true of these? Imagine they're simple numbers. If this is going to multiply out to 8, we'll say, and right now they're 4 and 2, and I double this one, I make this one bigger, what's going to happen in this one? It's going to have to get smaller. If this is 8, and this starts out as 4 and 2, 8 equals 4 times 2, right? And I double this one to 8, what has to happen to this one? It has to turn into 1. 1. It has to turn into 1. These two things are then what kind of proportional? Inversely proportional. So wavelength and frequency, let's write that down, are inversely proportional. As one goes up, the other goes down. So if that's true, which I said it is, and the laws of the universe say it is, which way should I draw my increasing wavelength arrow? Increasing frequency went from left to right. Which way should I draw my increasing wavelength arrow? Right to left. Good. Wow. Got a little bit less straight in the middle. Try again. That's still kind of garbage, but whatever. So that was increasing frequency. This one is now increasing wavelength. So just to make things abundantly clear, where would I find the highest frequency? I'm going to say light. Where would I find the highest frequency on the electromagnetic spectrum? This thing is called the electromagnetic spectrum.
Violet.
Of these, violet. In general, it'll be over here. Where will I find the longest wavelength? Of these, red, and in general over here. Are there other kinds of light besides those that we can see? What do we call the kinds of light that we can see? Does anyone know?
Ultravisible light.
Visible light. We call this visible light. Why do we call it visible light? What does that imply of the rest of the light? Invisible light. No one calls it that, but I'm going to. This is, all the other is called invisible. It's not called that. But I call it that right now because I want to make it clear that this light here we can see, the rest of it we can't. Does it still exist? Yes. How do we know? Well, let's move on to the next one. What would I call light that is just higher in frequency than violet light? No, stop just guessing and think about it. What would I call light that is higher in frequency than violet light? There's a word for it.
Ultraviolet.
Ultraviolet. Yeah, ultraviolet. We call this ultraviolet light. How do you know ultraviolet light exists?
Look, you just
What?
Because you said so.
Stupid comment.
What evidence is there that ultraviolet light exists?
You said so.
Burning.
What? Tegan?
Heated.
Oh, heated. What did you say, Justice?
Burning.
What kind of burning?
Sun.
Sun burning. You get a sunburn from the ultraviolet light. Ultraviolet light causes sunburns. That's one piece of evidence that you've probably experienced of ultraviolet light. What do I call? What might I call light that is below red? Infrared light. This is the one I would say, Tatum, is about heat. This is if you what evidence is there that infrared light exists? Some I don't know. Goggles. Some military boy or some, I guess, really avid hunter might have infrared goggles to be able to see things at night that could see human or animal body heat, because infrared, we all emit, all of us emit, and all mammals emit infrared light. You emit a little bit of visible light, but not nearly enough for our eyes to detect. But mostly the light that you emit is infrared light. And so even at nighttime, if you're wearing night vision goggles, which are infrared goggles, all those goggles do is take in infrared light and then jack up the frequency a little bit so that you can see it. So when you wear those goggles, you're seeing the infrared light. You're not actually seeing it, but the goggles are causing the infrared light to be increased in wavelength, increased in frequency so that you can see it.
Mr. Brown.
Yes.
And this is just the light spectrum, is what it's labeled.
This is called the electromagnetic spectrum. You could call it the light spectrum, people do. In fact, infrared light was discovered, I'm going to tell you how infrared light was discovered. I think it was William Herschel. It was either William Herschel or Isaac Newton. Listen, Isaac Newton invented the prism that allowed him to divide white light into these different colors. So this little part of the spectrum, the visible light, divides out, actually the whole thing divides out. If we have white light, sunlight coming in through the window, and we put a little prism that looks like this, here's some white light coming in, and out of that white light, it gets broken up into red,
Rainbow.
red, orange, orange. I'm going to do this whole thing again.
It's reflecting through.
Yellow, green, blue. I'm going to have to redraw my prism because these lines are so skinny. Blue, purple, 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 purple. So he had some sunlight coming in through his window, and the prism that he invented broke the white light up into these colors of light, and he thought, I'm going to put a thermometer in each one. So we put a little thermometer in each different color to tell which color of light was the warmest. And then he put one, he thought, outside of it to be the control. You remember controls in experiments? He put one outside to make sure that this one didn't change. And guess which one changed the most? No, the one right outside of it, because this one was in what part of the spectrum that we can't see? Infrared, which is a large part of what we call heat, is infrared light. And so he had this thermometer that he thought wouldn't change. He put it there as a control, but it did change, and it changed the most, by far the most. And that's because the prism broke up the light, not just into the visible spectrum, but into the invisible spectrum too. What goes below infrared light? You'll probably need your little chart for this. You might know it, I guess, but what is below, when I say below, in lower frequency, in greater wavelength than infrared light, what goes below that? There's a diagram. There's a diagram. Diagram on page. There's a diagram. There might be a diagram. I thought there was a diagram. There we go. On page 360, there's a diagram. On page 360, there's a diagram that you can use. Microwaves. Microwaves. There is, you can see from that diagram, I'm not going to draw because it'll make mine even messier, but you can see from that diagram there's overlap. Microwaves. Hey, guess what household appliance uses microwaves? The microwave oven uses microwaves. In fact, the microwave oven works on the principle that if light of a very specific frequency is applied to water, and only water, the water molecules, H2O, start to move a little bit faster, and we know from earlier in the year that faster movement of particles means more heat. And it only works, or it's supposed to only work, on water. It's tuned to the exact frequency of water's resonant frequency, so that'll heat it up. So is that a nice thing to put like a kitten in? No, because the kitten is made of mostly water. It'll heat up and then it'll melt. No, it'll pop. But the microwave oven has a certain frequency of water that does that. What else uses microwaves? Does anyone know anything else that might use microwaves? No, a dryer probably uses infrared light, but that's a good guess. Actually, this frequency here, the lower range microwaves and the upper range radio waves are where your cell phones operate. Cell phone. And a lot of digital communications, like the Wi-Fi in the school is in the microwave band. And then what's below microwaves?
Radio waves.
Radio waves. Obviously, radio waves are named because they're the carrier wave used by the radio in your car and we have one in our bathroom. I don't know who else does, but so you can listen to music in the bathroom. That's nice. Okay, going in higher, be quiet please, going in higher frequency, you remember that everything that you're saying is heard by the video, so just be careful and quiet. Higher in frequency than ultraviolet light, what does it say on the little diagram? X-rays, and you probably are aware of what X-rays are used for. And then higher in frequency than X-rays are gamma rays. Starting about here, partway through the ultraviolet, and then on, this is what we call ionizing, you should write this down, ionizing radiation. You remember talking about ions earlier in the year? What's an ion? Yeah, it's a particle, it's an atom that has lost or gained electrons. They're called ionizing radiation because these have the higher frequency and more energy, and also, let's write that down, that increasing frequency also means increasing energy.
Is gaining or losing what?
Electrons. But we're going to get to that in a second. So as we go from here to here, there's more energy also. How does the speed change throughout this? This is a trick question. How does the speed change from here to here? This is a trick question. It doesn't change. That's all going at the speed of light. All of this is going at the speed of light. All of it is going at the speed of light, which is c, which equals 300 million meters per second. All of it is going at the speed of light. But frequency increases as we go this way, and energy increases as we go this way. So after about this point, the radiation is what we call ionizing. It has enough energy that it can knock chunks off of molecules. Guess what you're made out of? Molecules, specifically DNA, which you don't want chunks knocked off of because that causes genetic mutation. So what's happening is when the sun, which emits light in all the spectrum, but our atmosphere absorbs all of this. But when the sunlight comes down, and you're sitting here, I'm going to draw somewhere else, you're sitting here, probably not completely naked, but mostly naked, and the sun is shining down on you, and you're like, I'm going to get a suntan. What's happening is your skin is being literally damaged. The ultraviolet radiation that isn't absorbed by the atmosphere is knocking parts off your DNA, which is causing your cells to die. And when your cells die, the rest of your cells are like freaking out, and so that causes the inflammation that is red, that is your sunburn. Listen, a corpse, don't try this at home, but a corpse does not get a sunburn. The red that is caused is not cooking you. The red that is caused is your body's reaction to, oh crap, everything around me is dying. The sun is killing me right now. I have to do something. So it's inflammation. So a sunburn is damaging your skin. And then why this is the part you like. Then 2 days later, you unless you're a pale little ghost, what happens 2 days after you have your sunburn?
Tan.
You get a nice little tan. And why does your body do that? Because I'm not going to let this happen again, is what your body says. I'm going to make sure that the next time I go out in the sun, I'm dark enough, I'm tan enough that my skin doesn't get damaged as badly. So your skin causes these changes, but this is bad for you. This is how people get skin cancer. Yeah, all of this is how people get, a lot of the times, about how people get cancer. So all of the x-rays, when you go in to get an x-ray, Colton, on your arm, when you go in to get an x-ray on your arm, or whatever, they don't just like throw you in the x-ray machine and turn it on, because that would make this same thing that's happening here for just a little time, but the same thing that's happening here happen all over your body. So they're very careful to cover you up. What did they give you, Colton?
The second time around, they didn't give me it the first time, was a little lead thing over my lap.
Yeah, why over your lap? Does anyone know?
Because it can sterilize me.
Yeah, well, not sterilize you, but it'll make your sperm turn into little freak mutant sperm. That then when you have a baby later, the baby will have problems, genetic deficits, and it's especially important for the sperm. Like it's not great for your stomach or your throat to have the X-rays go into them, but those things are not. The single cell, the sperm, the one sperm and the one egg come together to make a human being. And so if that one sperm gets messed up in a little bit of way, that human being is going to be messed up. If it happens in your throat, you've got hundreds of thousands of throat cells, and so one little cell getting messed up, that thing just dies, usually. So they cover up your reproductive organs, and sometimes they'll cover up your neck to where your thyroid gland is, because of a similar reason. But so you should do that too when you get the ultraviolet light. Good thing you already have this covered up, I would guess, when you're sunbathing. And then gamma rays, we don't really deal with gamma rays very much because they're just death rays. Like this is what, if you were going to make a ray gun, you'd make it emit gamma rays. Some kinds of nuclear radiation, you remember from chapter 18, some kinds of nuclear radiation emit gamma rays, that's what's super dangerous. This is very penetrative, and so it can go right through stuff. So then how come, if this is where the danger lies, is your cell phone dangerous? Someone's mom on Facebook is like, don't use a cell phone, it'll give you brain cancer. Which there is a little bit of evidence for that, but I'm going to talk about that in a second. But is the cell phone waves, are the 5G waves going to go in your head and make you a crazy person?
Yes.
No, they're not, because this is non-ionizing radiation. Except for this little bit right here, where the water which you're made of resonates, and then that's what makes a microwave oven work. But other than that, this is not unsafe, except the evidence suggests that your cell phone, especially when you're talking on it, which you don't do because you're not 65, but if you talk on your cell phone, the cell phone being hot, not the radiation from it, but your cell phone being hot causes some cell growth that can cause people to have brain cancer, the evidence suggests, which that's kind of scary. But it's not because of the 5G waves, it's because of the heat of the cell phone's battery.
Okay, so one thing I never quite understood is why when they take your x-ray, they're like, I asked them, I was like, so I see this little symbol, it's like a little radiation symbol. I was like, so what does that mean? They're like, oh, it just emits about the same amount of radiation as a microwave. And we're like, okay, whatever.
They probably didn't say that, because the microwave is non-ionizing radiation.
Then they hop behind the wall. And like,
and guess why that is? Guess why that is? And there's all these memes about it, and everyone's like, I'm so much smarter than ever. When I figure out that the x-ray guy is really trying to pull the wool over my eyes. No, why would they have to hide behind a wall?
I'm not sure they're around it.
Yeah, they're there, like Rhett's mom, every single day for 8 hours a day. So they don't want to have to wear the lead apron everywhere they go. And they don't want to be in the same room as it because they're there every day. You're there, well, I guess if you're Colton, 4 times a year on average. But if they're working there, they don't want to be exposed to it every single day. So they're not being cowardly. They're just trying to protect their gosh dang lives, Colton. Okay, last thing. Last thing. Shh. Okay, last thing. Also, furthermore, here's an easier answer, Colton. They don't need an X-ray, but you do need an X-ray. Okay, let's talk about real quick the difference between. Oh, I do want to talk about real quick. If you, Garrett, look at Garrett. Everyone, look at Garrett. Look at Garrett's shirt. What color is Garrett's shirt? Okay, we'll say it's orange. We'll say it's orange because it's easier. Garrett's shirt is orange. What is true of the rest of the visible light? So the white sunlight coming in through the window. Here comes white sunlight. Here it comes. Here's Garrett. This is what Garrett looks like. Just a potato. Here comes the white sunlight. Why does Garrett's shirt look orange? If the white sunlight is touching it, why does his shirt look orange? No, be careful. What is it absorbing?
It's absorbing the light that is.
Yeah, it's absorbing not orange, and it's reflecting orange. So here's your beautiful blue eye. Who's got blue eyes? I do.
Me.
Here's your beautiful blue eye, and what's going into your beautiful blue eye is what has the orange reflected off of Garrett's shirt. So what does that mean Garrett's shirt has done? All the other colors, the blue, the red, the yellow, I'm doing them not in great order, the purple, the green, all those other colors are absorbed by Garrett's shirt, and the orange is reflected, which is what makes our eyes see that Garrett's shirt is orange. What about my shirt?
Black.
Black. Where's black?